In a small English town in the Cotswolds, a 70-year-old woman named Sheila Irvine picked up a book and read it for the first time in years. For most of the past 4 decades, she had been losing her sight to a disease that had no cure. By the time she traveled to a hospital in London to take part in a clinical trial, the center of her vision was gone. Doctors placed a wireless chip, smaller than a fingernail, beneath her retina. A few weeks later, she put on a pair of glasses fitted with a tiny camera, and the letters on the page came back. The chip is called PRIMA, and the results of the trial Sheila took part in were published in the New England Journal of Medicine in October of 2025. Of the 32 patients who completed a year of follow-up, 27 regained the ability to read letters, numbers, and words. For the first time in medical history, an artificial device has restored what scientists call form vision, the ability to see the actual shape of things, in people who were legally blind. In the space of roughly 12 months between early 2025 and the start of 2026, scientists have restored sight to the blind, returned movement to the paralyzed, designed a custom gene therapy for a single dying baby in 6 months, cleared the hallmark cause of Alzheimer's disease from the brains of most patients in a major trial, and edited the DNA of living adults with one infusion to permanently lower their cholesterol. None of these are predictions. Each is a result that has already happened in real human beings, documented in peer-reviewed journals, or presented at the most rigorous scientific conferences in the world. The device implanted in Sheila Irvine's eye was developed at Stanford Medicine by ophthalmology professor Daniel Palanker and his collaborators. It measures 2 millimeters by 2 millimeters and is about 30 micrometers thick, roughly half the thickness of a single human hair. It has no battery and no wire running out of the eye. It works like a tiny solar panel. The patient wears a pair of glasses with a built-in camera. The camera captures the world and sends that image as invisible near-infrared light onto the chip beneath the retina. The chip converts the light into electrical signals, which are then carried by the patient's surviving retinal cells to the brain. The disease the trial targeted is called geographic atrophy, an advanced form of age-related macular degeneration, and it is one of the leading causes of irreversible blindness in older adults worldwide. Until this year, there was nothing doctors could do. 38 patients across 5 European countries were enrolled. 32 completed a full year of follow-up. 26 of those 32 showed what researchers defined as a clinically meaningful improvement in their vision. With the help of the camera's zoom function, some patients reached an acuity equivalent to 20/42, a level of sight not seen in their affected eye for many years. 19 patients did experience side effects, mostly related to the surgery itself, but almost all of those resolved within 2 months, and none were life-threatening. The lead investigator, Frank Holtz, of the University of Bonn in Germany, called it the first ever therapeutic approach to actually improve visual function in this group of patients. The device manufacturer has now submitted applications for approval in Europe and the United States. A higher resolution version of the chip with around 25 times more pixels has already been tested in laboratory animals. In May of 2025, a team at the University of Texas at Dallas published the results of another trial in the journal Nature. 19 people with chronic spinal cord injuries, some paralyzed for as little as 1 year, others for as long as 45, took part in a program that paired physical therapy with a small device implanted in the neck. The device delivered electrical pulses to the vagus nerve, timed precisely to the moments when patients made successful movements during their exercises. This combination is called closed-loop vagus nerve stimulation. After 12 weeks, the participants showed significant improvements in arm and hand strength and in their ability to perform the small tasks of daily living. What separates this trial from earlier work is that, on its own, the physical therapy did nothing. The lead researcher, Dr. Michael Kilgard, was direct about it. In stroke patients, he explained, therapy alone produces some recovery, and the vagus nerve stimulation multiplies that effect. For these spinal cord injury patients, therapy by itself produced no improvement at all. The gains came only when the nerve was stimulated alongside the movement. He called it groundbreaking, in his words, to be creating a gain, where there otherwise would be none. The results held regardless of the patient's age, regardless of how long they had been injured, and regardless of how severe the original damage had been. A larger pivotal trial with 70 participants across multiple American hospitals is now underway. In February of 2025, doctors at the Children's Hospital of Philadelphia, working with the Innovative Genomics Institute, built a custom gene therapy from scratch, designed for one specific child in 6 months. The child, an infant, had been born with a rare and usually fatal genetic disorder called CPS1 deficiency. His body could not safely process the protein in food. The therapy used CRISPR, a tool for editing DNA, but it was tailored to the precise mutation in this one baby's genome. The dose cost roughly $2 million. After receiving it, the child was able to tolerate a high-protein diet, and the doctors were able to have the dose of the drug he had been relying on. There were no severe adverse events. A few months later, in May, a teenager became the first person ever to receive what is called prime editing, a more precise form of gene editing, for a rare and often fatal immune disorder called chronic granulomatous disease. The function of his white blood cells was robustly restored to a level that researchers describe as potentially curative. Around the same time, a separate trial at the University of Minnesota used CRISPR to edit the immune cells of 12 patients with end-stage metastatic gastrointestinal cancers. One of those 12 patients experienced a complete response. Every metastatic tumor in their body disappeared over the following months, and at the time the results were published in the Lancet Oncology. More than 2 years later, the cancer had still not returned. In November of 2025, at a major cardiology meeting in New Orleans, researchers announced the results of a trial of a CRISPR-based therapy called CTX310. 15 patients received a single intravenous infusion designed to permanently switch off a gene in the liver called ANGPTL3. The expected outcome based on early planning was a 30 to 40% reduction in bad cholesterol. The actual result was a drop of around 50% in low-density lipoprotein and a drop of around 55% in triglycerides in patients on the highest dose. The reductions were sustained for more than 60 days. There were no serious drug-related adverse events. One infusion may, in principle, do what daily medication has been required to do for decades. Heart disease remains the leading cause of death on the planet. In July of 2025, the pharmaceutical company Roche presented data on a new Alzheimer's drug called trontinemab. It uses a delivery system known as a brain shuttle, which allows the drug to cross the protective barrier between the bloodstream and the brain far more efficiently than older medicines could. In the group of 54 patients receiving the higher dose, 91% saw the buildup of amyloid plaques. The protein deposits that are the hallmark of Alzheimer's fall below the threshold doctors use to define the disease after 28 weeks of treatment. 72% reached an even deeper level of clearance. The most feared side effect of drugs in this class occurred in fewer than 5% of patients. Alzheimer's currently affects more than 55 million people around the world. Alongside these chemical and genetic advances, machines are catching up to biology. In January of 2025, researchers at the Italian Institute of Technology and Imperial College London published a prosthetic hand that decodes signals from the spinal cord directly, allowing wearers a continuous, natural range of movement rather than a few preset grips. In September, Case Western Reserve University launched a clinical trial of a neuroprosthetic arm called iSense, which gives amputees both thought-controlled movement and a real sense of touch. In February, an electrical stimulation system called ARCEX, made by Onward Medical, became the first technology ever approved by the United States Food and Drug Administration specifically for spinal cord injury. It restores hand strength and sensation, and in some patients, partial bowel and bladder control. One patient regained that awareness 9 years after his original injury. The final area of progress is the one that has resisted medicine for the longest, which is aging itself. In July of 2025, the National Institutes of Health published a 20-year review of the largest controlled longevity drug study ever conducted. The single most powerful compound it identified was rapamycin, which extended animal lifespan by up to 28%, even when the treatment was begun in middle or late life. In a separate study published in the American Journal of Clinical Nutrition, daily vitamin D supplementation was shown to slow the shortening of telomeres, the protective caps on the ends of our chromosomes, by an amount equivalent to nearly 3 years of biological aging. A second team at Harvard independently confirmed the result a few months later. In Wales, a large population study found that people who had received the shingles vaccine were 20% less likely to develop dementia over the 7 years that followed. A modeling study from the Swiss reinsurance company Swiss Re estimated that the new class of weight loss drugs known as GLP-1 agonists, including Ozempic and Wegovy, could reduce all-cause mortality in the United States by 6.4% by the year 2045. Most of these trials involved between 10 and 40 patients. Some of the longevity findings come from animal studies, not from humans. The personalized gene therapy that saved one child cost $2 million to make. PRIMA, the Bionic eye, has been submitted for regulatory approval but is not yet generally available. Trontinemab, the Alzheimer's drug, is still in early-stage trials. Even the most spectacular CRISPR results have been observed in small numbers of patients, over follow-up periods measured in months, not decades. None of this is yet routine medicine. None of it is yet cheap. None of it has been tested at the scale of an entire population. Taken together, the pattern is clear. In a single year, sight was restored after macular degeneration, movement was regained after spinal cord injury. A custom genetic cure was built for one child. The hallmark of Alzheimer's was cleared from the brain, and the cause of heart disease was edited out of the liver. Each of these has moved cautiously from impossible into possible, from the language of hope into the language of evidence. What this means for the rest of us is harder to say than it sounds. None of these treatments are likely to reach most patients next year. The questions of cost and access have not been answered, but the diseases long believed to be permanent, blindness, paralysis, dementia, the slow erosion of the body by time, are not as fixed as they were thought to be. The boundary between what biology imposes and what medicine can do about it has shifted in 12 months, more than it has in some entire decades. The researchers working on these problems in laboratories from Stanford to Bonn, from Dallas to Philadelphia, from Tokyo to London, are no longer chasing an idea. They are reporting results. What is now known with confidence is that a wireless chip can restore reading vision to people blinded by macular degeneration. That a small implant in the neck, paired with the right exercises, can give back movement to people whose spinal cords were damaged decades ago. That a single infusion can permanently lower cholesterol by editing a gene. That the buildup behind Alzheimer's disease can be cleared from the brain. That a custom genetic therapy can be designed for one human being in less time than it takes to plan a wedding. What is not yet known is how widely these tools will work, how affordable they will become, or how long the benefits will last. Those answers will arrive in larger trials, in longer follow-up, in slower and quieter results.